Okay, so let's look at number 13 here. Sorry, number 12. Number 12 says using u substitution of u equals square root of x, the integral from 0 to 9 sine root x dx is equivalent to. So what's happening here is we're trying to convert everything in terms of u. So we'll go through u substitution, but we also want the bounds to be converted because we know that if our expression is in terms of u, our bounds is also in terms of u. So let's do this. Now they're telling us what our u value is, so we can just kind of move forward from that step, right? So if our u value is square root of x, that's the same thing as x to the what? 1/2, right? And if I want to go through my u substitution, I'm going to find my derivative and figure out what leftover expression I have to involve. Okay, so my derivative. What's my derivative here? Power rule gives us what? 1/2 x to the negative 1/2. Okay. All right, let me do some cleanup here. The same thing as 1/2 x to the 1/2. Same thing as 1/2 root x. If I cross multiply, I get dx is equal to 2 root x du, right? Okay, I'm going to make my substitution. Try to get everything in terms of u, so sine of u, and then dx gets replaced with 2 root x du. Okay. There's still that root x sticking out, but we'll deal with that later. But we do know the bounds have to be adjusted as well, because right now the 0 and 9 is in terms of what? In terms of x, right? So we're going to have to convert the bounds here. So that means when x is equal to 0, if x is equal to 0, and we know that u is equal to root x, that means u is equal to what for this bound? Still 0. Okay, so root 0 is still going to be 0. Okay. All right. If my original bound is x equals 9, and I want to get it in terms of u is equal to what? Root 9, which is 3. Okay, so I'm going to replace my bounds here. 0 stays 0. 9 turns into a 3. But there's one thing that's still sticking out here. I can replace this root x with what? U, because I have that substitution ready, right? I don't have to solve it. I just have to get it everything in terms of u, just enough for us to find the appropriate okay, so basically u sine u with 2 in front and then from 0 to 3. So looks like answer choice A is going to be the best fit. I can put that u anywhere. They just put it in front. Okay, any questions here? All right, number 13. Which of the following is a solution? So this is solving differential equations. You guys just took an FRQ quiz over these steps. So we're just going to go through our steps to separate our variables, get our y's on the left, x's on the right, take the antiderivative, plus c shows up, and then we solve for c. So first thing, I'm going to separate this to make it easier to work with. So I'm going to make this dy dx equals, I can separate this and make it what? E to the y times e to the x. I'm going to put it over 1, so I can cross multiply and eventually get my separation of variables. Okay, so here's my cross multiplying step. My dy dx's are lined up nicely. What's out of place though? Yeah, so I got to do what with it? Divide. Okay, so divide, where does it end up? In the denominator, right? Now this is e to the u. We don't do natural log for this, right? So where can I put this so I can use the appropriate integral rule? Where does this have to be? Numerator, right? So if I want to push this back up, it becomes e to the what? Negative y, yeah. Okay, so now we're ready to do our antiderivative. The right side is going to be nice because it's e to the x, e to the x. Now e to the negative y, that's going to be a little bit of u substitution. We can skip u substitution if we know that this is going to produce a what? The derivative will produce just a what? A negative 1. Yeah, so negative 1. I mean, if we want to go through our full u substitution, we can. You don't have to, especially if it's an easier u substitution. Basically, this is going to end up being e to the negative y times negative 1 because there's a negative 1 left over. So this ends up being negative e to the negative y as our antiderivative. E to the x will stay what? Just, yeah, integral of e to the x is just e to the x and then plus c. Yeah. Okay, so we're done with the calculus. Now to figure out how can we get y by itself. Yes. Yeah. So again, once we're at this stage, everyone can take a different step, and it all could be fine. You can solve for c first. You can solve for y first. You can work this halfway, and then solve for c, and then solve for y. So whatever step you take, just know that there's multiple ways to get to our y equals. So I may be doing it the way that may be different from what you prefer. So I'm going to multiply everything through by negative 1, just so I can get that e to that negative out of the way. So I get e to the negative y is equal to negative e to the x plus c. I'm going to do it a little bit differently than what I have in the key. I'm going to go ahead and take the natural log of both sides to drop that negative y down. So natural log of e to the negative y is equal to natural log of negative e to the x plus c. Okay. Natural log of e is going to go away. I'm just left with negative y is going to drop down. I can move that negative over. So negative natural log of negative e to the x plus c. Okay, so I have that equation. Again, may be different from yours. I'm going to go ahead and take now to solve for c. So I'll replace my y value with negative natural log of 4. I'm going to replace my x with 0 and see if I can get my way down to c. I can drop the negatives from both sides. And then we know about negative e to the 0 to negative 1. And these are both natural log. Natural log equals natural log. You can just drop the natural logs and then just solve for c. So I'm going to say 4 is equal to negative 1 plus c. So c is equal to 5. So now that I have my c equals 5, I'm going to take this, insert back in to my general equation. I'm almost done grading your previous FRQ and your differential equation problems look good. I think the only issue that I saw that students had was solving for C, and naturally that's going to just be a little messier. But you know, it's minimal points. The important thing is, can you separate the variables? Can you identify the appropriate integral rule? After that, the points are I would say up to this point where you can take the antiderivative and get that plus C to show up, you've earned majority of the points. And solving for C can be a little messy, but at worst, it's only 1 point off. Okay. All right. Next up, page 12. Okay, so we haven't seen area and volume in a while, so let's see if we can review some of those items. Okay, let R be the region in the first quadrant bounded by y equals x squared and y equals square root of x. So here's y equals x squared. Here's y equals square root of x. R is the base of a solid, so this is a cross-section problem. Whose cross-section is perpendicular to the x-axis? Okay, so first off, we got to decide which direction do we need to draw our base length. Is it vertical or is it horizontal? Okay, so x-axis is horizontal, right? Perpendicular is going to make it 90 degrees, so vertical. So the nice thing about vertical is that you don't have to make any adjustments to your equation. Your equation, the way that it's presented is fine. There's no need to get them to be x equals. No, that's nice. There's no need to change our equation. Okay, so let's do our base length. It's just top minus bottom. So what's the top of my length sitting at? X minus what? X squared. Okay. So the formula for squares is base squared, right? Length times width, where the length and width are the same. So we're going to build our area, which is going to be root x minus x squared squared. Okay, so that's the hard part. If you can get your area, then the rest of it is just to get to that third dimension, you just put the integral and dx and bookend on both sides. So now our volume is just, remember, there's no pi, right? There's no rotation. It's not this. It's not Washer method. There's no circles coming out of it. So it's just the integral. And then our bounds is going to be the furthest left to the furthest right. And you guys tell what those are. The furthest left is going to be what? 0. And the furthest right. Yeah, so root x and x squared, if you use your calculator, you can see that it's going to intersect at 1. So. And the rest just goes in your calculator, math 9. Okay, 15. The base of a solid, again, base of a solid. Graph is y equals sine of x squared between 0 and root pi. If the cross section, again, perpendicular to the x-axis, so pretty much the same scenario as above. Okay, so calculate is what the graph looks like. Sine of x squared. perpendicular to the x-axis. Okay, try that. See if you're able to set up, I mean, virtually the identical steps here. Same area formula, same orientation for your base. And basically drop the zero, right? The zero has no impact. Okay, any questions with 15? Okay, 16. 16 is only asking for the setup. Let's see if we can figure out how this is looking here. We have R being the region enclosed by 4 over x. 4 over x is a rational function that is going to be in the first quadrant here. So this is what the graph could look like. 4 over x has a curve like this. And then 5 minus x is going to be a linear function like this. Okay, this graph extends, but we're just showing the region where there's enclosed space. Right. We know we're doing with volume. We know this either disk or washer methods, because we see the word revolving. There's a circular rotation going on. And if that's circular rotation, there's going to be either circular disk or circular rings. Okay. We are rotating it about the y-axis. So this is my axis of revolution. All right. Based off of this, can we tell is it disk method or washer method? Washer, right? There's a gap, right? The only time that you're going to have a disk method is if your dotted line is up against the flat surface of the shaded region where you don't see any sort of a gap between the dotted line and shaded region. Obviously, there's a gap here. So we had to draw 2 radius, right? One that extends from the dotted line to the furthest shaded region, furthest boundary of our shaded region. That's big R. And then little r will extend from the axis to the closer. And then what adjustment do we have to make because we have horizontal radius here? Yeah, the equation has to be rewritten, right? They all have to be in a certain form. So this y-axis is just x equals 0. So that's 1. The linear equation, need to rewrite it. So initially it was y equals 5 minus x. If I solve for x, I get x equals 5 minus y. And then the curve, it is y is equal to 4 over x. If I cross multiply and then solve for x, I get xy is equal to 4. X is equal to 4 over y. So these are the equations that I want to be working with. Right? X equals, x equals, x equals. Okay, so let's build our big R here. Right minus left, what's the right endpoint of my big radius sitting on? X equals, yeah, 5 minus y. So it's 5 minus y minus the left endpoint, which is sitting on the, what's the left endpoint? 0, yeah, so 5 minus y minus 0. And that 0 will just go away, but I wanted to make sure that we knew our process of building our radius. Okay, little radius, what's the right endpoint of my small radius sitting on? 4 over y, okay, so it's 4 over y minus, what's the left endpoint? 0. Okay, again, these zeros will drop out, but want to make sure we know the process. So now our volume is pi integral big radius squared minus little radius squared. Make sure that we're squaring each of our radius separately. And then our bound is going to be our lowest to highest y value. So we can set these equations equal to each other and solve for y. We're going to get 1 and 4. So we know our bounds is 1 and 4. We just have to insert big R squared and little r squared and just have to match it up. No need to solve, just have to set it up. Okay. 5 minus y quantity squared minus 4 over y quantity squared dy. Okay, sorry, I think I'm running out of time here. So if you guys come get your phones, we'll continue, finish up the rest of the packet, hopefully tomorrow.
I've been doing 912 and repeating it, sir.